In this video, we continue with chapter 2.4. We take a look at the definition of LU factorization, where L is a lower triangular matrix and U is an upper triangular matrix. And we see how to use Sympy to find this factorization. So here's our definition of what we call the LU factorization, or sometimes the LU decomposition. So if the n by n matrix A can be written as a product of lower triangular matrix L and upper triangular matrix U, then A equals LU is known as the LU factorization of A. Note that the order matters. So you take the lower matrix first, multiplied by the upper matrix. Matrix multiplication, we can't do it in any order, so you can't say LU is the same as UL. So very important, the order is LU in our factorization, lower triangular matrix multiplied by the upper triangular matrix. So some important notes: not all square matrices have an LU decomposition. And sometimes you have to rearrange, what we call permuting, the rows of a matrix before obtaining its LU decomposition. So you might have to do some row swaps to get to the LU decomposition. Here are a couple examples of LU factorizations. So example A is a 2 by 2 matrix. And here you see we can break it down into this matrix with ones on the diagonal and one in the 2-1 position, and multiply that by the matrix with a 1 and -2 on the diagonal and a 2 in the 2-2 position. And so that's the product of these lower triangular matrices right here. With 1, 1, 1 on the lower part and the upper triangular matrix here. Similarly, matrix A here can be broken down as a product of a lower triangular matrix here and an upper triangular matrix here. And you can verify this multiplication by hand or checking in Sympy to see how we can break it down and factor this matrix. So let's do an example. We're going to use Sympy to find the LU decomposition of this matrix. So I am going to head over to Sympy and enter this matrix, and I'll go ahead and call it A, because I like to use A for matrices. So A equals matrix, and then, oh, I got to go back and look at my values. So 2, 0, 0, 0, -3, 1. And then my last row is 10, 12, 3. All right, and I can type A just to verify that's a match for the matrix I had over here in my example. All right, so to get the LU decomposition in Sympy, we need to name the objects to save them so that we can call them back up. So there are 3 things returned. You get the lower triangular matrix, I'm going to call that L. You get the upper triangular matrix, I'm going to call that U. And then you get what rows were swapped, so I'll call that R. Some people put the underscore here if they don't want to actually see those results. And then we say that's equal to A dot, and then our function is LU decomposition. Make sure you spell it right. And you put the parentheses to run the function. And then type U, here's our upper triangular matrix. Type L, here's our lower triangular matrix. If you want to see the row swaps that they had to do, they didn't have to do any here. So sometimes you might have to do some permutations to get row swaps in there, as we said. So Sympy will do those for us. And then you can verify. So we can verify if we do L times U, does that result match our A? And it does. You can also ask for a Boolean answer. So you can ask a true or false question. You can say, does A equal L times U, by using that double equal? That's a Boolean true false question for the computer program. And we get back out a true. So this is in fact true. So there is our LU decomposition. Let's see if I can copy and paste it. I don't think I can copy and paste it. So you can see it here. And then you could break down, here they are, L and U in your solutions. All right, we're gonna use the LU factorization of the coefficient matrix associated with this system to solve the linear system. Okay, so first of all, let's call our coefficient matrix, we'll call it B. So that is going to be 2, 1, 0 for the first row, and then 0, 1, and -1. So I'm just looking at the coefficients here. There was 2x, 1y, no z's, hence the first row. The second row, no x's, 1y, and -z, hence my coefficients here in the second row. And then the third row is -2, 1, and 1, because I have -2x, 1y, and 1z added up there. All right, I want the L and the U, my lower triangular matrix and my upper triangular matrix. So I'm going to head over to Sympy and let Sympy do this calculation for me. So I'm going to say B equals matrix. And my first row is 2, 1, 0. My second row is 0, 1, and -1. And my last row here is -2, 1, and 1. And then we can type just to verify. Matrix B is just what we had in our handwritten example over here. And I'm going to go through the decomposition. So I'm going to say, again, I'll do LUR equals B dot LU decomposition. So this will save new matrices L and U. And then I can check, here's matrix L, and here's matrix U. So I'm going to go rewrite these over in my other screen. So I got my lower triangular matrix, and then here was my upper triangular matrix. We can just click back in the previous tab to verify everything is a match. Okay, so now we can say, well, our lower triangular matrix times y is going to equal, we'll call this lowercase b, our column vector values here. So we get all these values, y1, y2, y3. You can see, okay, this is our column vector b over here. And so solving, we can see right away, okay, then y1 is going to equal 1 and y2 is going to equal 2. And then we see, okay, well, negative y1 plus 2y2, going from the bottom row here of our matrix L, plus y3 equals -2. So we can plug in our values here. All right, so -1 plus 4 plus y3 equals 2, or -2. So then this is going to be 3 plus y3 equals -2. So we solve that y3 is going to be -5. And then we can say, all right, well, our upper triangular matrix times x is going to equal y. So let's do those calculations. we've got our upper triangular matrix here. 2, 0, 0, 1, 1, 0, and 0, negative 1, 3 if I read off the columns. I'm going to multiply this by x. 1, x2, x3. And then the result should be what we called y, the 1, 2, negative 5. All right, so if we solve this, we get, all right, 3x3 equals negative 5. So we can say x3 equals negative 5 thirds. X2 minus x3 based on the second row there of our upper matrix, our upper triangular matrix. X2 minus x3 equals 2. So x2 plus 5 thirds equals 2. So then if we subtract 5 thirds from both sides, we get x2 equals 1 third. And then we know for solving for, what else we have? X1, we're going to use the top row. So we know 2x1 plus x2 equals 1. And so 2x1 plus 1 third equals 1. And then 2x1 equals 2 thirds. So x1 is 1 third. All right, so we have our solution here. So the solution to AX equals B is x1 equals 1 third, x2 equals 1 third, and x3 equals negative 5 thirds. All right, so that's how you can use the LU factorization, or we can call it the LU decomposition, to solve a system of linear equations.